This lesson deals with a common collector amplifier. You can find these notes in the ECE302 ebook in Chapter 5, starting on page 13. Here's a schematic of what's called a common collector amplifier. It's also called an emitter follower. I'll explain why that term is used once we get through the AC analysis. Suppose this time my beta F is 200, my VB on is 0.7, eta F is 1, and I have a 1.5 volt sine wave coming in. For the capacitors C1 and C2, I'm just going to say that they're big capacitors, and by that I mean that they look like short circuits in the audio band. In Chapter 10, I'll show you how to pick the value of these capacitors to meet whatever design specs you have for the bandwidth of your amplifier. Step 1 of our algorithm is to put a DC model in for each component. The capacitors are open circuits, so pretty much they disconnect this circuit from this side and from this side. So I just drew this part over down here. Drew the power supply twice. That's a nice trick for breaking the loops apart. I've got 20 volts and two 100K resistors. I've got the collector of the transistor, and then I've got the emitter back to ground with a 2K. My DC model for the transistor is a base emitter drop of VB on of 0.7, and then the current that's flowing in here now is 200 times the base current. If I take this part of the circuit and I Thevenize it and put it back, I've got a nice simple one-loop calculation. Let's remove this, find the open circuit voltage, which would be half of 20 volts because they have two equal resistors, and if you short this, you have 100K in parallel with 100K, which is 50K. Pretty quick equivalent circuit. Put that back in over here, and now I can calculate the parameters I need to verify that I'm in the active region. So here's I sub B, here's I sub C, and then what's down here is the sum of these two, which is I sub B plus 200 I sub B, which is 201 I sub B. If I go around this loop, I have only one unknown, I sub B. If I go around this loop, I've got two unknowns. I've got the collector emitter voltage and the collector current. So let's go around this loop here. The rise in voltage is 10, the drop is 50K times IB plus 0.7 plus 201 IB times 2K. I can now solve for I sub B. I sub B is going to be equal to 10 minus 0.7 divided by 50K and then divided by 2K times 201. This is going to dominate the denominator, but the actual value here is 20.58 microamps. Is that greater than or equal to 0? Yeah. That's our first check. The collector current is 200 I sub B, and that's 4.12 milliamps. And lastly, the collector emitter voltage, which is here, plus the voltage across this resistor has to always add up to 20. Take 20 volts and I subtract this drop, I got the voltage across the collector emitter. Drop across here is 201 I sub B times 2K. Is that greater than VCE sat? Well, we haven't stated what that is, but it's around 0.2 volts. So our assumption checks. Step 2 of our algorithm is to calculate the AC model based on the DC operating point. We've got an R pi and a beta F. Beta F, where AC and DC is the same, is equal to 200. R pi is eta F V sub t over I sub B at the Q point. That's equal to 1 times 26 millivolts divided by 20.58 microamps. That's 1.26 k ohms. My third step is to put in an AC model in. We're going to do this in the mid-band frequencies. What that's going to mean is that all our capacitors will look like short circuits. And our battery look like a short circuit because that's no change in voltage for a change in current. The same schematic I had on the previous page, except now I've got my V sub S and R sub S. Between the base and the emitter is R pi, which is 1.26 k. And then between the collector and emitter is the AC beta of beta F I sub B, which is 200 I sub B. I have a lot of ground symbols here, so let's see if we can clean this up a little bit. Make the picture a little bit smaller so I can show you the whole thing. Draw a common ground. Between 10K and ground I have V sub S. 10K between V sub S and the base. And then between the base and ground I've got 100K. And between the base and ground I've got 100K again from this R1. Between the base and the emitter, I've got 1.26K R pi. And then between the emitter and ground, I've got a 2K and a 1K resistor. And my control source is grounded on the backside of the arrow, and the tip is pointing towards the emitter. What's common between the output and the input now is the collector of the transistor, and that's why it's called the common collector amplifier. Let's calculate our 5 amplifier parameters of voltage gain, input impedance, current gain, power gain, and output impedance. Make this a little bit smaller so you can see the schematic and the analysis. So we're solving for V out in terms of V in, but what's V out? Well, it's going to be these two resistors in parallel and the current that flows into that parallel combination. We've got I sub B and 200 I sub B. That's 201 I sub B. Parallel combination of these two is 667. We have V out in terms of I sub B. We can see if we can find V in terms of I sub B. The rise in voltage here is V in. The drop is IB times R pi plus V out. That's this equation right over here. I sub B times 1.26K. V out is equal to 201 I sub B times 667. And now I have V in terms of I sub B. So V out is equal to 201 times 667. And then I sub B is V in divided by 1.26K plus 201 times 667. Now I can solve for V out divided by V in. It's going to be this term divided by this term. But notice that this term in the numerator is also in the denominator. Voltage gain is a little bit less than 1. The reason this is called an emitter follower, if we go back to the schematic, is that the output voltage is hooked up to the emitter to ground. The output with a gain close to 1 is following the input. The input impedance, go back to the schematic. Looking in here, I see these two in parallel, and then I see the equivalent resistance looking into these terminals, which is going to be V in, the voltage across here, divided by the current that's coming in. We have an expression for that from our last calculation. So Z in is the parallel combination of 200K resistors and the impedance looking into the base, and that's equal to V in divided by I sub B. And that's the expression right over here. V in divided by I sub B is this, 1.26K, and then plus 201 times 667. That controlled source effectively is increasing the resistance looking into the base terminals. That parallel combination is 36.5K. I showed previously that the current gain was the voltage gain times Z in over R sub L, 0.991 times 36.5K, and R sub L was 1K. So we do get a current gain of 36.2. Multiply the voltage gain times the current gain, and we get a power gain. We saw for the common emitter amplifier that we had a voltage gain and a current gain. For the emitter follower, we have just a current gain. The input impedance, though, of this common collector amplifier is much higher than the common emitter amplifier. We want the input impedance to be as high as possible so we don't form a voltage divider with our Thevenin resistance of our source. Finding Z out is also the same as finding the Thevenin resistance looking back into the circuit. So we're going to take the load off, set all the independent sources equal to 0, and then look into these terminals and find the equivalent resistance. Because I have a controlled source here, I'll need to apply a voltage, measure a current, or vice versa. To make things a little bit easier, let me do the following. Let me call the resistance looking back into the circuit this way, Z sub E, and that's in parallel with R sub E, which is 2K. To make the algebra a little bit simpler, if I pull this out, find the resistance looking back this way, and then put that in parallel with the 2K. I've got a 10K in parallel with 100K in parallel with 100K, and that's about 8.33K, a little smaller than 10K. I'm going to represent all of this by one resistor. So I've got I sub B, 200 I sub B, and I'm going to apply another test voltage and measure another test current and find the impedance looking into the emitter of the transistor. The current I test is entering the node. What's leaving the node is a minus 200 I sub B and a minus I sub B. I've got a minus 201 I sub B. What is I sub B? Well, it's the voltage here divided by the total resistance, 8.33K plus 1.26K. But the voltage here is the negative of V test. I sub B is minus V test divided by the sum of these two resistors. I can solve for I test 2 now. It's equal to minus 200 I sub B, but I sub B is equal to minus V test 2 divided by 8.33K plus 1.26K. V test 2 divided by I test 2 would be bringing this term over here and then bringing this in the denominator. The two minus signs cancel. We see that the value is 47.7 ohms. We're really dividing by beta F plus 1 the total resistance that's here. And that's one of the characteristics of looking into the emitter, and that's how the controlled source is affecting the equivalent resistance. The overall resistance is that in parallel with 2K, which doesn't change it very much. It's 46.6 ohms. The output impedance for the common collector amplifier is much smaller than the common emitter amplifier. This amplifier has some advantages for high input resistance and a low output resistance, because again, we form a voltage divider with the load that we hook back up here. The disadvantage is that we don't have a big power gain. We have a current gain and basically a voltage gain of 1. Given that our input is 1.5 times the sine of omega t, is the small signal assumption valid? Let's go back to the schematic on the bottom of page 14. And let's find the base emitter voltage. That's the voltage across here. That's going to be equal to I sub B times R pi, which is 1.26K. The current I sub B is going to be equal to the voltage across here, which is Vn, divided by the total resistance looking in here, which we found to be 135K. And then the voltage Vn is going to be V sub S times the voltage divider of Zn, voltage divided with 10K. Let's go back to page 17 where we have all those formulas. Base emitter voltage is R pi times I sub B. I sub B is Vn over Z sub B, which is 135K. And then Vn is a voltage divider with Zn and 10K and V sub S. Bring this over here. Zn was 36.5K, and then adding 10K to that, I get a 46.5K. And this ratio here gives me 0.0073 times V sub S. Although our input was pretty big, the voltage actually across the base emitter is quite small. It's 10.99 millivolts times the sine of omega t. Now this again can be somewhere between plus and minus 1, so the biggest it can be is a plus 1. And is that less than A to F V sub t, which is about 26 millivolts times 1. Yes, 10.99 milli is less than 26 millivolts. So we can now add our AC and DC results as step 4. Our output is equal to no DC, we blocked the DC. We get the voltage gain times Vn, and the voltage gain was 0.991. We now have to find Vn. It's going to be V sub S times the voltage divider of Zn over Zn plus 10K. And that's 1.167 times the sine of omega t. We have a voltage coming in, but the voltage coming out is a little bit smaller because we have a voltage gain less than 1 from V out to Vn. And this is the analysis of the common collector amplifier.